What's on the screen right now? That's right, I bet you didn't have any problem at all identifying these pictures as eyes, even though they all look incredibly different. If you showed this picture to, say, like a computer program or something, it may have trouble recognizing these as eyeballs because the colors and the shapes are all so different. But our human brain is hardwired to recognize eyeballs because we are experts at pattern recognition. We can see a pattern and identify it immediately. And so we like to apply the same sort of idea to organic chemistry. And let me show you what I mean. This is going to introduce the concept of functional groups. And functional groups are very important in organic chemistry. The idea is that molecules, when we talk about organic molecules, there's really an infinite number of them that you could draw, because I could draw some molecule and then just add one more carbon and it would be a new molecule. So in that sense, there's literally an infinite number of organic molecules possible. So what chemists realized what they had to do is start recognizing patterns within these molecules, start grouping these molecules into categories that allow them to predict past and future behavior. That is the goal. So the idea was to come up with this concept of the functional group, which is a pattern that seems to repeat itself in a lot of different organic molecules. Sort of like if you saw a creature, an alien creature, you could probably still recognize its eyes just because you know what the pattern of that part looks like on a living thing. Similarly, we're going to look for patterns within organic molecules and we'll recognize, oh, okay, that's the eyeball of this molecule, so on and so forth. So let's give a definition for functional groups. A functional group is a characteristic group of atoms or bonds with a predictable behavior. And I actually going to upload a list of functional groups that you should know, but I'll list them out here as well. So let's take a look at some examples of functional groups and their names. Okay, the first simplest functional group is just the alkane. It's sort of the absence of any functional group. So this is called an alkane. If you have an organic compound that has a CC double bond, a carbon-carbon double bond, we call that an alkene. And a compound with a carbon-carbon triple bond, that would be called an alkyne. All right. Another functional group we've actually already seen before in the last lesson was the alcohol. That's an organic compound that has the OH group in it. So if you see that functional group, that's called the alcohol. If you have an oxygen that is, instead of being bonded to hydrogen, is bonded to carbon on the left and right, that is called an ether. So an ether is similar to an alcohol, except instead of being OH, it's O and then more carbons. So that's an ether. If you have carbon attached to a halogen, like bromine, iodine, chlorine, that is called an alkyl halide. Also sometimes called a haloalkane. So don't be freaking out if you see haloalkane. They mean the same thing. Here's a fun one. This is a special type of ether. It is an oxygen in a three-membered ring. So it does meet the definition of ether because it's an oxygen with carbon on the left and right. But because it's in the three-membered ring, it gets a special name, and it's called epoxide. I want to put another one up here that's very, very common in organic chemistry. It's this hexagon with the three alternating double bonds. This is called benzene, but a lot of times benzene is incorporated into organic molecules, and so benzene itself becomes a functional group, and as a functional group, we don't call it benzene, we call it arene. So arene is that hexagon with 3 double bonds inside. It's called arene. It's a special type of alkene. That's why I kind of put it over here. Okay, let's do a couple more. What about if you have carbon attached to nitrogen, and the nitrogen can be attached to any number of hydrogens, and it still would be considered an amine or amine. So basically what I mean is look for a nitrogen that's either attached to carbon or hydrogen. So for example, we could have something like this, where we have a nitrogen that's connected to 3 carbon atoms. That is still considered an amine, even though it doesn't have any hydrogens attached. But this is also an amine. It's got nitrogen connected to carbon and hydrogen, so they're both called amines. Then there's a lot of functional groups that have a CO double bond. It's very common. So if you have a compound that has a CO double bond, and this is of course a CO double bond, we have carbon here and oxygen here. And if connected to the carbon of the CO double bond, you have carbon on the left and right. So 2 carbons, one to the left and one to the right. That is called a ketone. And if you have a CO double bond and one of the atoms is a hydrogen, that is called an aldehyde. If you have a CO double bond and one of the atoms happens to be a OH group, that is called a carboxylic acid. Be careful, it's no longer called an alcohol, even though you see the OH group. Because it's an OH next to a CO double bond, it gets a new name, carboxylic acid. If you have a CO double bond next to a nitrogen, that is called an amide. And one more, CO double bond next to oxygen on one side, that is called an ester. Okay, and there's going to be some more functional groups on a handout that's uploaded right beneath this video. It's an instructor download that's available to you that it just has a list of all the functional groups. Okay, so you should start to memorize these functional groups, just like it's going to become automatic for you, just like you never had to memorize what an eyeball looked like. You just had to see enough eyeballs to start making patterns for yourself. And so we're going to do the same thing here with these functional groups. At first, all these names are going to be confusing. You've probably never seen these words before, but soon, I promise, it's going to become more automatic. We're going to start using that in our language as we talk about these molecules. So let's take a look at a very complex organic molecule. This molecule is called strychnine. You may have heard of strychnine before. It was hundreds of years ago, it was used as a poison to assassinate people who, they didn't want around anymore. So they'd kill them by giving strychnine, which is a poisonous organic compound. Strychnine today is used as a rat poison. So it comes from a tree. It's like a chemical found in like the nut of a tree. And it's very, very poisonous to mammals. So they can give it as a rat poison. Okay, but as beautiful as this compound is and as scary as this compound is, you can see it has a high level of complexity, a lot of rings connected to each other. That's a very complex molecule. Let's just recognize the functional groups that are buried within the molecule. Okay. So let's take a look at this nitrogen. What functional group is a nitrogen? Is this an amine or an amide? Remember, an amine is a nitrogen attached to carbon or hydrogen, versus an amide, which is a nitrogen that's attached to a CO double bond next door. So is this an amide or an amine? This is an amide because we've got a nitrogen and then a CO double bond next door to it. So this functional group right here is an amide. What other functional groups do we see in this molecule? Oh, well, we see the ring, the benzene ring, the 6-membered ring with the 3 double bonds inside. What did we call that? That was called arene. And so we're kind of like identifying the body parts of this molecule. Like this might be the nose and this might be the eyes. And we're just recognizing these body parts in this compound. What about this nitrogen up here? So remember, nitrogens can either be part of amides or amines. Is this nitrogen next to a CO double bond? No, it is not. So this nitrogen here, is going to be the amine. All right. Here we have a CC double bond. What do we call that? That's called alkene. All right, and I see another functional group here. This oxygen here, what is this guy? Is this an alcohol? No, we don't see OH. I mean, we see H here and O over here, but they're not attached to each other, so that isn't an alcohol. What is this? It's an ether, because we have oxygen connected to carbon on the left and right. So that is an ether. All right, cool. And that's it. That's all the functional groups in this molecule. We wouldn't identify alkane as being in this molecule because alkane is just the absence of functional groups. So if we looked at the molecule and we didn't see any of our functional groups, then we would call it an alkane. But as long as there's just one other functional group, like you wouldn't call this alkane. It's just too specific. So we just ignore that. Awesome. Okay, there'll be more practice for naming functional groups on your quiz after this lesson and also on problem set 1. There's a few more cool compounds where you can identify some functional groups. Now, it can be tiring to write out functional groups, so chemists have developed a number of abbreviations to help simplify drawing organic structures. And so you're not ever going to be required to use abbreviations, but I sometimes use abbreviations to save time, so I just want you to be aware of those abbreviations. So let's talk about that on the next page. So abbreviations. Okay. Let's take a look at an example of a molecule here. Okay, this molecule here can be abbreviated. We have this arene over here, and if you have an arene just sort of hanging off of a molecule on the end, with nothing else attached to it, you can abbreviate that as PH for phenyl. Although it is an arene, it is a very plain arene in that there's nothing attached to it. It's just sort of dangling off the edge. And so if you have an arene that's just dangling off the edge, we call that phenyl. And then over here on this side, on the other end of the molecule, we have a CH3 group, and that is a methyl group. And we can abbreviate that ME for methyl. So if we redraw this molecule with abbreviations, now we can just draw it like this, PHOME. And that represents the exact same molecule. We just abbreviated the arene on the left as PH and the methyl group on the right as ME. Perfect. Now, one important note about abbreviations is that they can only be used on the ends of molecules. They can't be used in the middle. So abbreviations are only for so-called terminal groups. That is, groups at the ends of molecules, either in the left or the right, the top or the bottom, but they can't be sandwiched in between things. So let's take a look at an example here. This molecule can be abbreviated. We have a chlorine attached to a butyl group. So the butyl group has an abbreviation BU. And I'm going to give you a list of all the abbreviations. There's not that many of them. There's only like 10 or so that you're going to see in this class. But the 4-carbon chain, just like the 1-carbon was called methyl, the 4-carbon chain is called butyl. And so we could abbreviate this as just CLBU or CL line BU. It's okay if you want to include the bond connecting the abbreviation to the rest of the molecule. You can use a line or you can choose not to use a line. It's your choice. All right. So this would be a good example because the butyl is on the end. But let's take a look at a bad example. So let's see something that's incorrect. Let's do chlorine, a butyl, and then put another chlorine at the end. So in this case, we could not use the butyl abbreviation because butyl is now in the middle. It's not on the end. So you could not write this. That would be unacceptable because the butyl is in the middle. Let's take a look at another bad example. How about, let's do one similar to the first molecule we looked at. Okay, so this is similar to the first molecule we looked at. There's only one difference, and that is that I added a bromine onto my phenyl group. So what you could not do then is now you can no longer use the phenyl abbreviation, because now the phenyl is not on the end. It's not dangling off the end, but it's sandwiched between stuff on the right and left. So you could not write this. That would be unacceptable, because now the phenyl is sandwiched. Okay, so you can only use abbreviations for when they are on the ends. Here are the most common abbreviations that you should know. And they are ME is one of the most common. It stands for methyl. ET stands for ethyl. These are all common side chains. IPR, that stands for isopropyl. Notice that the I is kind of superscript. BU, that's butyl. TBU, again, kind of like the IPR, it's like a superscript T. That stands for tert-butyl. You remember these groups from our naming chapter. PH, which stands for phenyl. And you'll sometimes see OAC. That stands for acetate. And that has the following formula. Has a negative charge. It's the acetate group. So there's also uploaded along with those functional groups is some common abbreviations that you should know. All right. Sweet. Okay, those are abbreviations. And again, you're never forced to use abbreviations, but I sometimes use them, so you should know what they represent. All right, now we want to go on to the last topic of today's lecture, which is resonance. Resonance is something you may have learned already in general chemistry, but we want to review it here, so this may be a review. Let's take a look at an example molecule here. Let's take a look at the carbonate anion. If you remember, that's one of the polyatomic ions from general chemistry. And so let's draw actually the Lewis structure for the carbonate anion. It looks like this. And what we can see is that the carbonate anion can engage in resonance, meaning that we can delocalize some of the electrons in this molecule like this. So we can move the lone pairs on that right oxygen towards the CO double bond and kick electrons up onto that oxygen. And if we do that, we're going to draw a resonance arrow, which looks like this double-headed arrow. Hopefully this isn't completely foreign to you. You should have learned about this in general chemistry. And then we can draw another resonance structure. Where the CO double bond has moved. We can draw another resonance structure. Now we can move this oxygen's lone pairs into the double bond, further delocalizing electrons. If we do that, we get this structure. Okay. And those are all the possible resonance structures for the carbonate anion. And then also what we like to do is add some brackets to show that these are all resonance structures. All right, so what's interesting to note here is that resonance is the delocalization of electrons and it's stabilizing. So we'll just say that. Resonance is the delocalization of electrons, and it's stabilizing. Resonance is a good thing. It stabilizes the molecule. Now, what a lot of students think is that what this means is the electrons are moving around, bouncing around, but that is not the case. It turns out that these electrons are existing in all places simultaneously, that the true form of carbonate is not any one of these forms, but rather a resonance hybrid, which is a blending of all of these forms. This molecule is not fluctuating randomly between these three forms, but rather it's existing as all three forms simultaneously. So the resonance hybrid is the average of all resonance forms. And that's the true picture. So if you're going to draw the actual true picture of carbonate, it would look like this, where I'm going to put kind of a dotted line to represent that the double bond sometimes exists in that area, but not always. And then I'll put a 2- charge in the upper right-hand corner to show that this molecule always has a -2 charge. It's just not clear exactly which atoms are bearing the -2 charge at any one given time. So that is the resonance hybrid. So now we want to talk about the 3 rules of resonance, because what I'm going to ask you to do in this class is sometimes to draw resonance structures of organic molecules. And so it's really easy to draw resonance structures as long as you can count to 1, 2, 3, which we're going to do on the next page. So let's take a look at the 3 beautiful rules of resonance. Okay, the 3 rules of resonance are as follows. Rule number 1, you can only move electrons in pi or p orbitals. What that means is that you're only going to be able to move lone pairs and double or triple bonds. You're not going to be able to move single bonds or anything else like that. Pi and p orbitals is going to limit you then to moving lone pairs and double or triple bonds. Number 2, don't violate the octet rule. When you move electrons in pi or p orbitals, you should not end up by giving 10 or more than 8 electrons to any atom. Similarly, you should not move electrons such that you leave any atom with less than 8 electrons. So a good resonance structure will not violate the octet rule. Now, rule number 3 is actually a but for rule number 2, in that carbon and boron can have an octet violation. Specifically, they can have less than 8 electrons. Nothing can ever have more than 8 electrons for resonance purposes in this class, but carbon and boron can have less than 8. So carbon and boron can have less than 8 electrons. So these are the 3 rules of resonance. Now let me give you 5 scenarios that resonance is likely to occur. So these are 5 patterns you want to look out for in organic molecules that will tell you, okay, there's a resonance structure available for this pattern, okay? Scenario 1 is the most common situation that you'll encounter. Scenario 1 is you have an organic compound that has a polar pi bond. Remember that a pi bond is a double or triple bond, and a polar pi bond is a double or triple bond between 2 atoms with a difference in electronegativity. Remember, I think it was 2 lectures ago we looked at that electronegativity values. And so if you have a difference in electronegativity between the 2 atoms that are connected, that is said to be a polar bond. So a great example of a polar bond would be a carbon-oxygen bond, and we can make that a polar pi bond by making it the CO double bond. Very, very common type of polar pi bond. And so we can draw a resonance structure whenever we have a polar pi bond by moving electrons onto the more electronegative atom. So the pi bond electrons move on to the more electronegative atom, and that's going to create a new resonance structure that looks like this. We're going to get an additional lone pair up on that oxygen. It's also going to get a negative charge now. And since we're moving electrons away from carbon, that's now going to have a plus charge since it only has 6 electrons now. So that is scenario 1, polar pi bond. Move the electrons of a pi bond towards the more electronegative atom of the polar pi bond, and that's going to create a resonance structure. Notice that this obeys all the rules. We are only moving the pi electrons of our double bond, and we are not violating the octet rule. Well, technically we are, since we're leaving this carbon with only 6 electrons. However, rule number 3 says that's okay. Carbon and boron can have less than 8 electrons, so this carbon with 6 electrons is okay. Scenario 2. This is another very common situation, and that is when you have a lone pair next to a pi bond. And so let's take a look at an example of what this looks like. We could have an amide, which is a nitrogen next to a CO double bond, one of the functional groups that we had already seen. And the resonance structure you can draw if you have this is a lone pair next to a pi bond, move the lone pair towards the pi bond, and break the pi bond, kicking electrons towards the faraway atom. If we draw this resonance structure, we'll find it looks like this. We've created a negative charge on the oxygen since we've moved electrons towards it, giving it a lot of electron density. And the nitrogen has a formal positive charge now also. You can use the formal charge formula to prove that to you. All right, scenario 3 coming up next. Scenario 3 is an empty p orbital next to a pi bond. Okay, an empty p orbital is just an atom that has less than 8 electrons. So if you ever have an atom with less than 8 electrons, it will always, in this class, have an empty p orbital. So I can draw an example of what this would look like. Let's put a positive charge on carbon. I'm just drawing in all the hydrogens, just so that we can see all the hydrogens there. And so if we look at this carbon here, you can see that it has only 6 electrons, right? This carbon has 1, 2, 3, 4, 5, 6 electrons because each bond is worth 2 electrons. So that carbon does not have a full octet, and you can also see that with the positive charge there showing that it's electron deficient. So what we can do is then move the pi bond into that empty p orbital, just like this. And if we do that, we'll move the pi bond over to the right. I'll draw in all the hydrogens again. And since we moved electrons away from the left side of the molecule, that is going to leave a deficiency of electrons on the left side, and so we're going to have a positive charge on the left now. Notice that charge should always be conserved. So if the overall charge of a molecule is neutral, then all the resonance structures will also be neutral. See, for example, this first scenario, this molecule was neutral, so the other resonance structure is also neutral. Even though it has a minus and a plus, they cancel each other out such that the overall charge is 0. And similarly, in scenario 3, we have an overall positive charge, so that makes sense that after the resonance structure, we still have an overall positive charge. Another thing to notice here in scenario 3 is that none of the single bonds changed at all. All of the hydrogens stayed exactly in the same place before and after the resonance structure, again showing that we're only moving electrons in pi or p orbitals. We're not moving any electrons in sigma bonds. We're not breaking any single bonds. All those hydrogens stayed exactly still. Okay, that's scenario 3. Let me just scoot this over a little bit because there's just 2 more scenarios to talk about. Okay, scenario 4. Scenario 4 is a little bit more rare, It's an empty p next to lone pair. Empty p next to lone pair. And so let's see what that would look like. Let's do an example with boron, my favorite element. Okay, so this boron here, I'll draw some lone pairs on the oxygens. Okay, I drew in all the lone pairs in this compound here. This boron in the middle has only 6 electrons. Each bond counts for 2 electrons, so we have 1, 2, 3, 4, 5, 6 electrons on that boron, so that boron has less than an octet. So because the boron has less than 8 electrons, it is going to have an empty p orbital on that boron, and indeed it does. Now look what we have. We have some lone pairs next to empty p. So we can move those lone pairs towards the empty p orbital and create a resonance structure. Assign the formal charge would look like that. And empty p next to lone pair. And finally, scenario 5. Scenario 5 is a simple one. It's just pi bond next to pi bond. Pi bond next to pi bond. So let's take a look at an example of that. If we just have a pi bond attached to another pi bond, we can draw a resonance structure where we move electrons towards the other pi bond. And we dump electrons as a lone pair on the end of the second pi bond. So if we do that, that'll put a lone pair and a negative charge on the right side of this molecule. And since we moved electrons away from the left side of the molecule, we'll be left with a positive charge there. So that's pi bond next to pi bond. So those are the 5 resonance scenarios. Now, I'm going to warn you here. Watching me do this, it is very natural at this stage to be a little overwhelmed and a little bit confused. What's really important is that you actually get some hands-on practice doing this. When you watch me do it, it can seem overwhelming. But when you work it out and try it yourself, you'll feel much, much, much better about it. Okay, so promise me you'll go right after this video and take a look at problem set 1. There's some practice drawing resonance structures. And as you draw the resonance structures, try and identify which scenario you are using when you draw that resonance structure, because it's always going to fit one of these 5 scenarios. And my OCD is going a little crazy. I need to underline scenario 3 and scenario 4 just so I can be consistent. Okay, last thing I want to talk about today is how to determine the major resonance structure. Because you can end up with a situation where we draw a bunch of different resonance structures, but which one is the best? And so there are 3 rules that help us decide which resonance structure is the best. Let's talk about that. So this section is called How to Determine Major Resonance Structure. Major meaning the most stable. Okay, how to determine major. So let's take a look at an example. Let's take a look at a tricky example here. Okay, here is a molecule. Can we draw a resonance structure for this molecule? Do any of the scenarios apply? Do we have a polar pi bond? Yeah, we do. We have a CN bond. That's a polar pi bond. That's pretty good. Do we have a lone pair next to a pi bond? Careful. No, we do not. We do have some lone pairs, but they are not next to a pi bond. They are directly attached to a pi bond. Next to a pi bond would mean a lone pair like over here. So be careful when we talk about lone pair next to pi, that we're not talking about lone pair directly attached to an atom that's part of pi, okay, because that's different. How about a lone pair next to empty p? Ah, that's a tricky one. You may have missed that one. How many electrons does this carbon have? Let's count. So 1, 2, 3, 4, 5, 6. This carbon only has 6 electrons, which means it has an empty p. What about this nitrogen here? This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So that nitrogen has 8 electrons. But the carbon only has 6 electrons. Aha, so we do have a lone pair next to an empty p. So we can draw a resonance structure. Simply move the lone pair towards the empty p. And if we do that, we get a resonance structure that looks like this. We can calculate our formal charges. They look like that. Okay. And so this was scenario 4, which is lone pair next to empty p. Okay. Now, which one of these resonance structures is best? Is this resonance structure on the left really good? Or is this structure on the right really good? And so to figure that out, we need to look at the most important rule for determining the major resonance structures, and that is rule number 1. Rule number 1 must be obeyed above all else. So if there's a way to obey rule number 1, this is always going to tell you who the major resonance structure is. And rule number 1 says max number of atoms have an octet. That is the most important rule. So looking at these two resonance structures, which one has the maximum number of atoms with a full octet? It's the second one. Remember, in the first resonance structure, this carbon only had 6 electrons. But look, in the second resonance structure, the carbon has 8 now. 1, 2, 3, 4, 5, 6, 7, 8. And the nitrogen also has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So the nitrogen also has 8 electrons. So the second resonance structure is the major resonance structure because it satisfies rule number 1, which is the maximum number of atoms have an octet. All right, let's take a look at another example. Let's take a look at carbonate. Okay, we can draw a resonance structure with a polar pi bond. We can move electrons up onto the oxygen. I should probably include the charges here. We've got 2 negative charges. And if we do that, we get and this is going to be scenario number 1, which is polar pi bond. Now, rule number 2 says you would like to minimize formal charges. So after you make sure that you pick so the most major resonance structure is going to be the one where all the atoms have an octet. However, the second thing you want to consider is minimizing formal charges. You want as few formal charges as possible. So in that case, the first structure here is going to be major because you would like to minimize the number of formal charges. In the first structure, we only have 2 formal charges. But in the second structure, we have 4 formal charges. So that's the second rule. Okay, and then the third rule, the least important rule, but sometimes used to break a tie, is the following. So let's say we have this compound here. And we could draw 2 resonance structures. We could draw a resonance structure where we move electrons onto the oxygen. This is polar pi bond. Or we can draw another resonance structure with our polar pi bond where we move electrons onto carbon. And let's see those 2 possibilities. So if we go down and move electrons onto carbon, we'll get this structure here. And if we move electrons up onto oxygen, we'll get this structure here. Okay, so among these three resonance structures, which one is the best? The middle one, because only the middle one satisfies rule number 1, which is the maximum number of atoms have an octet. In option 3, the carbon does not have an octet. And then in this option over here, the oxygen doesn't have an octet. So that means that the very best is going to be the middle. But comparing the left and right, which one is better? And it turns out that the rule number 3 helps us figure that out, which says, put the positive charge on electropositive atoms. And put negative charge on electronegative atoms. And so remember, to determine who's electropositive and who's electronegative, you can look at your electronegativity table, which we looked at back over here. And we can see that we're comparing oxygen and carbon, and oxygen has a higher electronegativity than carbon. So we prefer to put a negative charge on oxygen versus carbon. So if we go back to where we were, which resonance structure puts a negative charge on the most electronegative atom? That would be this one over here, since the negative charge is on oxygen and the positive charge is on carbon, which is more electropositive. So this would be okay. Still not the best because we don't have octet satisfied, and this one would be the worst since we don't have our octet satisfied and we're putting the charge on the wrong atoms. And this is, by the way, this is scenario 1 also. Polar pi bond. All right, cool. So that's how you can help determine the major resonance structure. We'll do more practice like that just so that you get a feel for it. One more thing I want to mention is the effect of resonance on hybridization. When I first learned this, I thought this was kind of interesting because it was something I hadn't thought of. Effective resonance on hybridization. So let's take a look at an example. Okay, here's a beautiful amide. And let me ask you a question. What is the hybridization of this nitrogen? Remember, in order to determine the hybridization, we calculate the steric number. Do you remember the formula for the steric number? It's the number of bonds, sigma bonds, plus lone pairs. So if you look at this nitrogen, there's 1, 2, 3 sigma bonds and 1 lone pair. So the steric number is 4. So we would say that that is sp3. Or I'll say it appears sp3. But now let's draw a resonance structure. So we'll move the lone pair towards the pi bond. Remember, that's scenario 2, lone pair next to pi. And if we do that, we'll get the following resonance structure. Now let's look at the hybridization of that nitrogen. So again, we'll look at the steric number of this nitrogen, and to determine the steric number, we count the number of sigma bonds plus lone pairs. This is only counting as 1 sigma bond, even though it's a double bond. Remember, that only counts once. So we have 1, 2, 3 sigma bonds and no lone pairs. So now the steric number is 3, which means it appears sp2. So how do we solve this issue? Because remember, resonance structures are not vibrating between these two resonance structures, but rather it exists as a single hybrid. So what do we say this nitrogen is? Is this nitrogen sp3 or is it sp2? Is it sp2.5? No. The rule is Any sp3 atom that participates in resonance is sp2 at all times. Any sp3 atom, I'm putting sp3 in quotes here because it's not really sp3, that can participate in resonance is always sp2. That's a rule. So let's take a look at a few examples here. Okay, here's a molecule. If you look at this oxygen, if you look at it, you might think it's sp3. After all, you count the number of sigma bonds, 1, 2 sigma bonds, plus the number of lone pairs, 3, 4. You would expect this molecule to have a steric number of 4 and be sp3 hybridized. However, we can draw a resonance structure where we move electrons, lone pair next to pi. That's supposed to be a plus charge there. And we get this structure here. And now if we look at the steric number of this oxygen, you can see that it's sp2. It has only 1, 2 sigma bonds and 1 lone pair with a steric number of 3. That's sp2. So our rule says that this oxygen must be sp2 at all times because it's participating in resonance. So it's sp2. Let's take a look at another example. Okay, here's a fun one. One of these chlorines in this molecule is sp3 hybridized and the other is sp2. Can you tell which chlorine can participate in resonance? That's right. The chlorine on the right can participate in resonance because it is a lone pair next to a pi bond. However, the chlorine on the left has lone pairs, but it is not next to a pi bond. It's actually 2 away from a pi bond, which is not a valid resonance scenario. It must be exactly 1 away for it to participate in resonance. So that means the chlorine on the left is sp3 because it cannot participate in resonance. And the chlorine on the right, since it's a lone pair next to pi, can participate in resonance, so it's sp2. Let's do one more example. Okay. If you look at the hybridization of this sulfur, you might think it's sp3 because you've got 1 sigma bond, 2 sigma bonds, plus 2 lone pairs, which is a steric number of 4, which is sp3. However, it can participate in resonance. We have a lone pair next to pi. To give us a resonance structure that looks like this. And now you can see that sulfur is sp2 hybridized. So remember, if an atom can participate in resonance at any time, it's sp2 all of the time. So sp2 on that sulfur. All right, cool. All right, hopefully that all makes sense. Now we need to do a lot of practice making sure we're confident about drawing resonance structures. And so problem set 1 will help you with that. Okay, that's it for now. Bye.